Well, it is 3:10, so we're going to get started. I just want to say good afternoon and welcome to the Iowa Nutrient Research Center Fall Seminar Series. I am Dr. Kay Stefanik, Assistant Director of the Iowa Nutrient Research Center. Our seminar series this fall is going to be on trends in surface and groundwater nutrients across the United States. And we are going to have speakers from Nebraska, from the Lake Erie watershed, Chesapeake Bay watershed, as well as Mississippi River watersheds, talking about trends in nutrients. Before we get started today, I just have a few housekeeping items. First, this is a hybrid session, so there are participants online as well as some people in person in Ealings Hall. For those of you who are online, please type any questions you have into the chat box to me, and I will read those off to Dr. Gilmore at the end of his talk. And for those in person, Dr. Matt Helmers will be facilitating the discussion and allowing you to ask questions at the end of the talk. We are also going to be recording this webinar as well as the rest of the seminar series and posting those to the INRC website for later viewing. Now, for today's talk, we have with us Dr. Troy Gilmore. He is the Associate Professor at University of Nebraska-Lincoln in both Conservation and Survey Division in the School of Natural Resources, as well as in the Department of Biological Systems Engineering. And today he's going to be talking about nitrate in Nebraska with a focus on nitrate levels in the state, as well as impacts on groundwater. So with that, the floor is yours.
Thank you. I guess you see the slide presentation.
Yes, we can see it, and we can hear you as well.
Great, thank you. Well, thank you everyone for joining today, taking a little time out of your day to listen to this talk about nitrate in Nebraska. I will be coming at this as more of a groundwater hydrologist, so focusing heavily on the groundwater nitrate picture for Nebraska, starting with kind of a statewide view, and then just sharing a few highlights of some recent research projects, including some groundwater nitrate and age information that we near a groundwater mound. We'll talk more about what that mound is and so on. Something we're calling the Red Pivot Project, and then also some groundwater and surface water interaction where we have high nitrate groundwater feeding Bazille Creek up in the northeast part of Nebraska. So that's what we'll cover today. This timeline that you see on the left side was developed by Crystal Powers at the University of Nebraska. Obviously, it's pretty small here. You can't see all of it, but I just picked out a few of the dates here just to highlight some of this background of 100 years of Nebraska nitrogen. And the first one is a little bit self-serving because I'm part of the Conservation and Survey Division at the University of Nebraska. This is Nebraska's State Geological Survey, and we were established. We have a history that goes past 1921, but specifically the focus on studying Nebraska water came about at that time. As early as 1940, there were nitrate issues being identified around poorly built wells. Human health was on the radar at that time. And then in the 60s, we're seeing a water quality survey that was showing these areas where groundwater nitrate was above the present day drinking water standard of 10 parts per million. In the 1970s, we had a major development in Nebraska where we had natural resource districts that we call NRDs established. These are local management areas that have locally elected leaders and a lot of local control, including being able to raise funds to facilitate the management of natural resources and water. They started widespread nitrate testing, and that continues to this day. In the 80s and 90s, there was continued work on human health, some of the early groundwater quality policies, and then something called the Bazille Triangle was an area of emphasis, and you'll recognize that name Bazille later in the talk as well. By 2013, we have reports of more than a third of the irrigated acres with showing groundwater above 10 parts per million. And then in very recent years, there have been people digging into some of these nuances around, for example, high nitrate in groundwater potentially releasing or um, different forms of uranium or some kind of interactions with uranium. There's more human health studies going on, including perhaps mixtures of nitrogen, forms of nitrogen, and other agrochemicals. And so there's a long history of nitrogen issues and work going on in Nebraska. And also on this timeline on the right-hand side are lots of things that have been going on the more of the ag side on nutrient management and so on, best management practices, which is a little not so much my area of emphasis. Underlying all of this, of course, is, from my perspective, groundwater underneath our state. So I have a couple slides just to remind people of how much groundwater we have in Nebraska. Using the High Plains Aquifer as our kind of primary discussion point because it covers most or underlies most of the state. You can see that Nebraska has the very thickest portions of the High Plains Aquifer extending saturated sediment as much as 1,000 feet thick and out underneath the Nebraska sandhills. So certainly thicker aquifer than, for example, Texas in the south. In terms of aquifer volume or volume of that saturated thickness, Nebraska holds almost 70% of the volume in the High Plains Aquifer, and you can see the smaller proportions for the other states listed here. Groundwater levels are relatively stable in Nebraska. We're often asked if the aquifer is drying up, and you can look on the map on the left and see places where they started with thinner aquifer and have had groundwater levels drop in those areas, whereas Nebraska has a bit of a different picture there. If on the right-hand side, if we look more specifically at Nebraska, pre-development is roughly the 1950s. Comparing that to the spring of 2022, this is a pretty steady kind of map that we see annually where we do have areas in the western Nebraska where there have been significant declines shown in red. And then there are other areas where groundwater levels have actually risen since the 1950s. Particularly, you can see a bold kind of blue area in the south central part here that we'll talk about a bit more later in this talk. But this is an area where canals, which are fed by diverted Platte River water, have a very leaky bottom, and that contributes a lot of groundwater recharge and has actually resulted in a rise in groundwater levels in that area. There are, of course, a lot of different, landscape features and so on that influence the recharge and the replenishment of groundwater. And then there are also a lot of different environmental factors, as everyone probably on this call knows, controlling groundwater nitrate. But just to highlight some big picture factors, this land cover map of Nebraska gives us some good insight with all these green areas, green shaded areas representing agricultural fields. The large light colored area out in the western part of Nebraska those are the Nebraska sandhills, which of course do not support with very sandy soils, do not support so much the row crop agriculture. Second factor is irrigation density. Here you can see in this eastern part of Nebraska, particularly in this Platte River Valley, really high density irrigation. A lot of that historically was flood or surface irrigation in a number of areas along the river valleys. Some of that is changing more to the center pivot, but nonetheless, when you combine the addition of irrigation water and the unpredictability of precipitation, you enhance that possibility of nitrate leaching below the root zone. And then depth to groundwater, or you could say vadozone thickness, is another major factor, and it's a bit of a proxy for travel times, right? So in this valley where you have shallow groundwater. These are some of the areas where nitrate was first seen in groundwater, elevated levels of nitrate. And there has been some work with changing management practices and so on that have shown some modest improvements in these areas where you have a relatively rapid response because ground nitrate that infiltrates and makes its way to the water table relatively quickly. Those management practices can show up the benefits of those management practices can show up more quickly in those locations. You can see we have some very thick vado zones in some of these areas of over 200 feet, which and there's a lot of work. I won't talk about it today, but there's a lot of work being done by Dan Snow and others in Nebraska who are really doing a lot of deep coring and other work to try to quantify the presence and concentration and mass of nitrate being stored in these thicker vado zones so that we can anticipate that moving toward the groundwater. But these different factors kind of collide and coincide and produce this kind of map, which is our groundwater nitrate concentrations in recent years. You can see some of these swaths in the river valleys. We have sandy soils up in the northeast and some of these river valleys in the west as well, where we have high nitrate concentrations. Another view, kind of a pixelated version, is this plot, which shows or graph that shows nitrate data from the Nebraska Groundwater Quality Clearinghouse from the last couple decades, and it's showing the median value for each of these townships. But you can see some of those same swaths there as well. And then lastly, we have this visualization that was done by the Nebraska Department of Environment and Energy in their most recent groundwater quality report. And this was, they used kriging for this, but they are using a lot of historical groundwater data here, along with other predictors, to try to do a spatial prediction of groundwater quality, particularly nitrate. And they're now moving toward using machine learning and additional layers of information, spatial information to, with the intent of creating tools that, say, a private well owner could use to understand some of the risk of having high nitrate concentrations in their particular area. So this was a kind of a first kind of illustration that is leading to more detailed and complex modeling that the Department of Environment and Energy is doing, which is pretty exciting. In terms of domestic wells, drinking water in Nebraska is primarily coming from groundwater. And so we have concerns about private or domestic wells. We have concerns about public water supplies as well. This particular plot comes from a report from the Water for Food Institute at the University of Nebraska. The green line shows you the number of wells sampled, which are hovering around 400 in recent years. And then the blue shading is showing nitrate concentrations in these wells on average hovering around 7 to 8 milligrams N per liter. So we have certainly elevated nitrate concentrations showing up in private or domestic wells. The Department of Environment and Energy plots similar data up, but using the median nitrate N here. You can see that number comes out lower, but they're pointing out also a slight upward trend with that solid black line on this left figure. In the lower right, you can see the distribution of the samples that were used for this analysis, and it highlights, the difficulty when you have domestic wells. There's certainly no requirement of testing these in Nebraska, so getting a representative and long-term data set is difficult, and I guess one of the reasons that I won't be using the word or won't be talking in detail about trends so much because of some of the complexity of the data available. Moving on to the public water supplies, this map really kind of pulls together a lot of information, but using this quarterly sampling requirement as kind of a proxy to illustrate the need or the challenges that a lot of small communities are experiencing in terms of nitrate in their groundwater supplies. So when they have greater than 5 parts per million, they need to move to quarterly sampling. Currently in this map, 157 out of about 550 systems are required to have that quarterly sampling. On the extreme end, they may need to install treatment, which, as we know, is an expensive proposition, especially when you have small communities. In between that, they may do things like install new wells. Some locations, they are using low nitrate concentrations out of one well, mixing that with another well that may have higher nitrate concentrations in order to bring that down into compliance. But this is a big picture of the public water supply challenge in Nebraska. Focusing down into this south central part of Nebraska where we see several of those stars, and also we see this triangle here where they have treatment. This is the area of the first study that I'll talk about today and highlight just a few of the results that we have studying nitrate down in this area. And this is an area that is in the vicinity of this groundwater mound. This groundwater mound is, as I mentioned earlier, a result of the water leaking through the canal system. The water diverted from the Platte River goes through these canal systems and has a very high recharge rate. There's also a reservoir as well that's leaking on the west end of this. But this mound is developed over decades, as you saw in an earlier plot. But the area where we conducted this study was right on the boundary of two natural resource districts, Tri-Basin and Little Blue natural resource districts. And a couple of the things that we were focused on were using groundwater chemistry and isotopes to investigate kind of where that Platte River water, which is now groundwater, the transport of that, the extent of that, and then also the spatial patterns of groundwater nitrate. And so this is Michaela Cherry working here to collect an age-dating tritium helium sample with some of the agency folks looking on there. We had some really good collaborators from the agency. These are the well nest kind of network that we had to work with. A number of these wells existed already, and others we added additional wells so that we would have nested wells. Most of these have at least 2 different depths with relatively short screened wells. And we like to have 3 if we can, and we have that in many of these locations. Moving on to the geology of this area, this is that center B to B prime cross section that you see there. The dashed line that's running left to right there is the water table, and you can see it crossing the different materials that are in the subsurface here, silt, and then beneath that sand, and then some sand and gravel in the yellow shaded areas. This cross section is the same as the last one, but we've now shaded and filled in the saturated areas in the subsurface with these 2 different colors. On the right-hand side, you see the dark blue colored saturated areas, and we collected groundwater samples from the different wells in this area. Those are noted by the red dots there. And one of the things that we measured were stable isotopes. And this dark shaded area had groundwater that had stable isotope composition that was consistent with the local precipitation source. So that tells us that precipitation or locally derived groundwater was a source of recharge perhaps. When I say locally derived groundwater, I'm saying that that was pumped for irrigation and then replenished, came back through and replenished the aquifer. So that area was isotopically consistent with local precip, while this aqua shaded area to the left was consistent with Platte River water. And so that what that tells us, or what we were trying to delineate there, was the amount or the kind of extent to which the Platte River water was replenishing and contributing to this mound in this area. The numbers that you see next to the red dots on this cross section are groundwater ages in years. And what we see, if you look at the shallowest wells, moving from left to right here, what you see are groundwater ages that are less than 70 years old all along the top. This makes a lot of sense because groundwater is recharged from the top and is generally younger toward the top of an unconfined aquifer like this. However, we also sampled some of these deeper wells, and you see some very large numbers here in the thousands. These were age dated with using carbon-14 method, and so we have ancient groundwater kind of involved in our modern water cycle here. Moving on to the nitrate situation in this particular cross section, what we see are nitrate concentrations that are consistent with those groundwater ages that we just saw. So groundwater in the shallower wells that comes from recharge that happened in the last 70 years or so, those are the wells that are showing the elevated nitrate concentrations. Not all, but most of them. And whereas these deep wells are showing very low background concentrations of nitrate. So we have this vertical variation of nitrate concentration in the aquifer, which is a pretty common observation in these kinds of agricultural areas, but they also complicate significantly looking at things like trends in these areas where you may sample at the same location, but depending on the depth of that well, you could have very different nitrate concentrations. Of course, the variation in nitrate, both vertically and kind of spatially or in the map view, are dependent on a lot of different things. Like we mentioned earlier, land cover being one of those, and then the transport of that nitrate. One of the things that we were looking at in this study was whether or not nitrate was being transported across, for example, the boundary between the different management districts, which was this dashed line here. That was one of the things of interest. So the time of travel across there was of interest. But nonetheless, the hydrogeology and pumping for irrigation are major factors in the movement of the nitrate. And then there's this question of, how quickly can nitrate be removed from a system once it's been introduced. And that brings us to this bottom issue where nitrate basically has removal mechanisms of leaving with the water. So through pumping or discharge to a spring or a stream, or it's consumed by denitrification. And so these are the things that we were working with the agencies to, especially in the removal component here and denitrification concepts, working with the agencies to help them understand those concepts to aid their monitoring. But as part of the conversations, Marty Stange, who is at the city of Hastings, we were talking about some of those spatial variations of nitrate. And this is one of the things that Marty said that really caught my attention. He was talking about a particular area in their management district that did not have much groundwater nitrate. And he said that that's an area with red pivots. And I was not familiar with the term red pivots at that time. But that kind of observation got us thinking about visual water quality indicators. And was an interesting topic. I mean, in this image, you probably have a sense of whether or not anybody in this image is getting ready to jump into this impoundment. Probably not. We kind of have an instinctive reaction to the algae there. And Marty's comment kind of got us thinking about whether or not there's a possibility we could have some visual indicators above ground that tell us something about nitrate concentration in the invisible groundwater below ground. And so this also happened to coincide with COVID, where we had students who were kind of stuck in apartments and so on. And it was an opportune time to get onto Google Earth imagery and zoom in and just see if we can look for these so-called red pivots. And in this particular image, it shows kind of the difficulty of doing that. We thought about maybe we could have some image analysis or something to do it. But if you look closely at this image, you can see a dark line that looks like a center pivot span going across here, but actually that's the shadow. And below it is the more silver color of the actual pivot itself. Nonetheless, Michaela and another worker, Bethany, went through about 700 different center pivots in this study area, looked at them in this aerial imagery, and classified them, whether they looked shiny, like this center pivot, where you see this galvanized metal look, looks nice and new and shiny, or in the other extreme, whether it looked quote unquote red, which is really a rust staining or a patina on this center pivot. And then we had an intermediate classification of a partially rusty pivot. In this case, you have drop nozzles, so the water is spraying on the towers or the lower part of the center pivot and staining that. But we had this intermediate class of partially rusty pivots. So what we're looking here is really a deposit that's a result of the groundwater that's spraying out of these nozzles and depositing on these center pivots. And the result of this, when we pulled together the nitrate data for all of these different center pivots, that was stored in the groundwater quality clearinghouse, we got this plot, which is a summary of this red pivot or rusty pivot project. On the right-hand side, you can see where pivots that were stained with rust had consistently low nitrate concentrations and significantly lower statistically than the no rust pivots. Obviously, if you have a pivot that looks shiny and new, that there's no guarantee whether it's high or low. There's a lot of variability there, right? But the rust and even part rust pivots tended to have lower nitrate concentrations. So that we also map this up spatially. There's I would say, a kind of swath of this dark colored area on this upper map showing part to full rust center pivots, and that correlates somewhat, not perfectly, with nitrate concentrations that are lower, the lighter colored swath in this lower plot, to give you kind of a map view of our observations. But the question was, is there a plausible explanation for rusting pivots being correlated with lower groundwater nitrate? And some of you that are familiar with redox, you've maybe already gone down the mental path of how this might work. But just quickly, we have, if we look at this sketch of the subsurface with that Vado zone, then the water table and the groundwater, and we have the potential for biological activity down in the aquifer. We have microbes down there that need to survive or want to survive. And they have electron donors, potentially something like organic carbon, and then there are dissolved solutes that they use as well as electron acceptors. And they step through these different solutes in a sequence that's energetically favorable to them. And so the first thing that we'll do is use oxygen. This is why we end up with anoxic groundwater sometimes when we sample it. And then this is basically the redox ladder here, right? So you use oxygen and then nitrate is consumed next, manganese, and then they start interacting with iron. And this is the iron that can lead to rust stains on bathtubs and sinks and also center pivots. If it goes beyond this point, then you may get, it may start interacting with sulfur, and that's when you get that rotten egg smell when you pump groundwater or maybe walk through a swamp or whatever. But uh, this is a kind of plausible reason that these rust stain pivots could be correlated to lower nitrate concentration, because by the time we start getting that iron being present, there's a good chance that nitrate has already been consumed. I will say just anecdotally that this has been a really interesting project. You can see the story map at the bottom here at that address, go.unl.edu/rusty pivots. I've been able to talk to a lot of different people and bring up redox for the first time without using that term. And it's actually generated a lot of conversation because people are driving by these rust stained pivots every day out in the rural areas where they have irrigation and maybe haven't noticed them before. And I think it's a win if they're now seeing those as an indicator of something about the groundwater quality below, which has been kind of exciting to see people tune into this idea. There are, of course, a bunch of caveats. Some of these pivots are just old and rusty on their own. Other ones, there are manufacturers that paint the metal, and as it would turn out, some of those paint them kind of a dark red. We obviously had a limited spatial extent of about 3 counties in this particular study. You can have long screened wells for irrigation wells. It's common. So you could be pulling groundwater from different parts of the subsurface. So you could be actually mixing maybe groundwater that where nitrate has been removed through denitrification, but you may also be pulling from another layer where there's higher nitrate, for example. And then there's commingled irrigation where some operators have the option of switching between surface or groundwater depending what's advantageous for them at the moment. So see, these are some of the caveats, but we also have some funding to expand and to start to address some of those. One way that we are expanding is we're working on a phone app where you could easily collect data. Once I've talked to colleagues and also my kids are sick of me looking at rusty pivots. There's also kind of interesting because some of them are kind of a greenish color, some of them are almost black, and then there's the classic kind of red rust color as well. But we're trying to make a way where it would be very easy for people, including maybe agency staff, as they go around and sample to record their observations. We have the opportunity through some funding to extend the spatial extent up into the Northeast Nebraska area. And then we also think there's opportunity if we do some more verification of this and work around some of the uncertainties that I can imagine a spatial layer to add, for example, to Department of Environment and Energy's machine learning approach to interpolation and prediction of nitrate concentrations. So this expanded extent is kind of important because that'll be the next visit that we make for this final study that I would like to share a few results from. And this is the Brazil Creek watershed. I mentioned earlier the Brazil Triangle. That was the early name for the focus on this area because there's been high nitrate concentrations for quite a long time up in this area. But we were getting into the issue of Brazil Creek surface water having high nitrate and the contribution of groundwater nitrate to that. So that'll be the next topic we cover. And this isn't, like I said, this is an area where there was there have been there's been work going on for a very long time up in this area, right? And so having the introduction of groundwater age dating into this area, um, there had been a little bit of it done in wells back in the 1990s, but doing this at the stream interface added a kind of a new element of establishing kind of realistic travel times uh, over which we could expect management changes in, for example, nutrient management to have an effect on the groundwater in the area and Bazille Creek specifically. Just to give you an idea of the watershed that we're working in, we're around 800 square kilometers, dominated by row crop, especially in the southern part. Pastures tend to be kind of along the stream itself, and then also in the northern part. The aquifer is less than 90 meters. That the thickest part of it's in the south, and it thins toward the north. And then the base flow index here is about 0.5. So roughly 50% of the stream flow on an annual basis is coming from base flow, which is primarily going to come from groundwater. The flow is from south to north here, with center that's shown here as a USGS gauge on the northern end of our study area. And so we did a lot of surface water sampling here. We focused especially on the base flow conditions here to make that connection with groundwater inflows and influence on this stream. When we sampled at Bazille Creek, at that northern outlet, we saw mostly steady and elevated nitrate concentrations, about 8 milligrams N per liter. And we also saw, even though we focused on base flow, we also looked at how nitrate changed with flow, and it tended to decrease as flow increased, suggesting that high nitrate groundwater inputs were especially dominant at low flows and maybe being diluted at higher flows. Moving downstream or upstream, I should say, to a tributary called Spring Creek, we did the same frequency of sampling near the outlet of Spring Creek. This is a view where you can see in the foreground very quickly here that we have a nice large seep along this edge. And Spring Creek, not too surprisingly given the name, has a lot of groundwater nitrate input. And excuse me, we saw pretty consistent levels of 12 to 16 milligrams N per liter at this site. Just to give you a flavor of kind of the extreme other type of tributary that we worked with is the SWT3 tributary. And here you can see the nitrate concentrations kind of bouncing all over the place here, suggesting that we're having, even though the max value here is close to what we saw at Spring Creek, that this is probably something more than just a very steady input of groundwater nitrate here. It's much more dynamic, maybe some overland flows or potentially even other source of contributing here. When we look at kind of a summary of all of that sampling across the watershed, on the left-hand side here in the blue dashed outline, these are sites along the main channel, starting on the upstream end on the left and downstream to center Nebraska on the right of those three. When we can see that decreasing nitrate as you move downstream. So a lot of high nitrate inputs in the upstream end. Similarly, sites that were on tributaries are shown on the right side here in that same upstream to downstream direction. And you can see that each of these tributaries has its own characteristic. It's kind of interesting. Spring Creek there is highlighted, and you can just see that steadily high nitrate concentration, while the SWT3 is here with a lower nitrate, but a lot of variability. So these were the tributaries and the dynamics of base flow nitrate that we were seeing across the Brazil Creek watershed. The next thing that we were interested in, and this is the last bit that I'll cover, is the groundwater discharge to streams and the nitrate that was entering the streams through along with that groundwater. So we're kind of looking at the stream here as a way to evaluate what is coming out of the aquifer, an easy way to access groundwater essentially without having to drill wells all over the place. And we can theoretically be intercepting a wide range of groundwater flow paths at any point in the stream, with potentially younger groundwater coming in along the edges, uh, potentially deeper, longer flow paths contributing toward the middle of the stream right at the same time. The way that we do this is to use some small probes, and it also helps if you have really great students. I should have had a picture of Galen Richards in this slideshow, but he was the master student who led a lot of field work under a lot of different weather conditions out here. Sydney Corcoran is shown here. She was an undergrad who was really helpful to Galen throughout this project. This on the left-hand side is a picture of the type of probe that we use. And there's a very small screen, about 2 inches or 5 centimeters at the bottom of this probe. We push this into the stream bed about 1 to 3 feet, depending on the situation. And we can sample groundwater in the stream bed just before it emerges into the stream. Usually we try to organize or sample in kind of these orderly transects across the stream. The reason for that is that we often see distinctly different chemistry and groundwater age. Even when we're sampling maybe only a meter apart in the stream bed, the groundwater might be substantially different across even this small stream. This is one example of several sites where we did this kind of work. This is a small headwater tributary. We had nitrate concentrations around, on average, of about 13 milligrams N per liter here. And you can see the probes that we had temporarily installed in the stream in order to sample that groundwater. And what you see in this plot are the groundwater ages associated with those different sampling points across the stream. And that fits, in this particular case, it fits that model of younger groundwater coming in closer to the banks and then older groundwater coming in toward the center. And so overall, we saw tracer-based groundwater ages ranging from 12 to 24 years at this particular site. The other sites had similar types of ages in orders of years to decades. So we could communicate then with managers in the area, the natural resource districts, and other stakeholders in the area about how long it would take for groundwater to move from the water table through the aquifer and to come out in this particular stream, somewhere in 10 to 30 years, say, is kind of the time frame. The other thing that this really tells us is that we have a lot of different historical influences being imposed on this stream all at the same time, because these these groundwater flow paths are coming from different distances and so on, and also taking longer times. I've seen a couple questions pop up, and maybe I'll answer them at the end. I have just a couple more slides. So kind of the summary for Brazil Creek is that we were able to communicate about how groundwater is traveling years to decades. This is consistent with a lot of other shallow superficial aquifers or unconfined aquifers. But we could also communicate about those different dynamics of different tributaries and so on as far as the surface water quality. We could communicate about effectively the storage of nitrate in this aquifer and how it will be transported with groundwater and how it's contributing to stream water nitrate levels. Just a quick wrap-up slide. We do in Nebraska have some significant challenges in terms of domestic well owners, public water supply systems. Um, we have these same drivers, a lot of those things we know about, right, in the big picture in terms of what is driving nitrate variability and the lag times that still apply. Um, but we are excited and interested in different monitoring methods that can help us analyze data that we do have for understanding and predicting risk around these issues. Um, there are a couple of slides. I think I'll turn it over to the host if they want to cover these last couple of slides, and then I can do questions.
Yeah, that sounds good. Uh, so if you would like to look at any of our previous seminars, they have been recorded and they can be found on the INRC website, either at cals.iestate.edu/INRC/video, or you can use our QR code. And that is also where this seminar and the rest of the seminars in the series will be posted. And could you go to the next slide? And our next seminar is going to be on October 9th from 3:10 to 4 p.m. Central Time. And the speaker is Lori Sprague with USGS, and she is going to be talking about long-term nutrient trends from the Mississippi River Basin into the Gulf of Mexico. All right, so I am seeing 2 questions in the chat. Maybe we'll start with those and then we'll go to those in person in Eelings. So the first question I'm seeing is there any data on N2O concentrations in the groundwater sources?
I don't believe we collected any in these particular studies. No.
Right. Which stable isotopes have been used to determine the age of water?
The stable isotopes were used just for more delineating the source of the groundwater. And so those would be like O18 and deuterium. And then in terms of the isotopes used for age dating, the young groundwater, so less than 70 years or so, we used tritium helium age dating method for that, those estimations of age, groundwater age.
And we'll do one more question from the chat and then we'll move to in person. So can you clarify in the red pivot example, did the lower nitrate, higher iron groundwater differences come from different ages of the groundwater or another factor?
Oh, that's a good question. We did not, we did very limited age dating along those transects that we showed. I guess I've just thought of that pretty much through the redox lens more than age. I mean, there are, denitrification rates that apply in terms of maybe there are cases of slow removal of nitrate gradually, depending on the situation in the aquifer. But I guess I just think of it more as a redox question.
All right. And are there any questions from the in-person audience?
Question? No, no questions in here.
No? Okay, then we have one more in the chat. So how have agencies been using any of these results for management decisions?
That's a great question. I will say that in the case of the um, the study that we did around the groundwater mound, that was at an agency border, right? And there were questions kind of on both sides of that border about the movement of, say, nitrate across that border. And there were differences in, for example, you have the groundwater mound where you have groundwater levels rising in the west, and you have actually a slight bit of depletion out east of where I showed on the map. And so there were questions about how those changes over time could have been influencing the movement of water and or nitrate across those borders. And while I can't say that the groundwater ages that we provided were like exactly used in a very specific um, policy, I would say that being able to show those ages and really demonstrate the rate, the types of distances that groundwater will move in a given year at this more kind of like county level scale as opposed to the direct vicinity of a well, being able to show that kind of regional timescales of groundwater movement were really helpful for those conversations between those different management districts and to kind of settle some of those questions that they were having. Um, I will say maybe another way that has yet to occur, but one of the things that we're working toward is using those groundwater ages, particularly up in the Brazil Creek area, as either calibration or validation for coupled groundwater surface water models. And so those kinds of modeling efforts will play in, I think, to management decisions in the future. So those are some of the ways that have potential for that.
All right, and we'll take one last question so I don't hold you here too long, but it looks like in the groundwater mound, concentrations are around 30 milligrams N per liter. Is that to say that the concentrations in the Platte River and the canals are at those concentrations?
That's a good question. Um, and it's from Francois, no doubt. So that's a good question. Platte River is generally not at 30 milligrams N per liter. I would say that it could also be from irrigation water applied that's coming out of those canals as well and having high recharge rates. That would be my first response to that.
All right, well, thank you so much for your presentation and for all of those who have joined us online and in person. And please join us for our seminar in October.